Welcome to Emergency Control Functions, part of the Fire Alarm and Signaling System Design Fundamentals online learning series from NFPA. Click Next to get started. This learning series covers a range of topics related to fire alarm and signaling system design. By the end of this lesson, you should be able to determine correct fire alarm and signaling system outputs given inputs from select initiating devices. Describe how a fire alarm and signaling system can send outputs to perform emergency control functions. And describe considerations and requirements for the selection and placement of initiating devices within HVAC equipment, fire alarm equipment used for door and shutter release, and initiating devices used to initiate elevator recall and elevator shutdown. You can click the button on screen to repeat these navigation instructions. If you're ready to begin, click Next. The menu bar at the top of the window provides important functions to help you as you complete this lesson. Select Menu to see an outline of the lesson that displays your progress. Navigation provides instructions for navigating this lesson. If you need to close the lesson, select Exit to leave and save your progress. Select the collapsed menu icon on the left to show and hide the transcript. This lesson includes knowledge checks and short activities designed to assess and apply your learning along the way. What do you think? Questions give you a chance to think about a topic before we discuss it. Activities ask you to apply what you've learned in a practical scenario. There will be a 10-question assessment at the end of the lesson. You must achieve a passing score to complete this lesson. Remember that what do you think and activity questions are not graded and will not affect your final score. This lesson is divided into 5 sections. First, we'll briefly cover the basics of emergency control functions in a fire alarm and signaling system. Second, we'll explore the process for mapping inputs and outputs that relate to emergency control functions. Finally, you'll go through 3 sections covering requirements and considerations for heating, ventilation, and air conditioning, or HVAC equipment, doors and shutters, and elevators. This lesson should take about 60 minutes to complete. Click Next when you're ready to proceed. As you've seen, a fire alarm and signaling system controls components of its own system and supervises components of other systems. But a fire alarm and signaling system can actually control the function of other building systems. Because this control will occur to increase building, fire, and life safety during an emergency. These are called emergency control functions. Recall how initiation, supervision, and notification work in a fire alarm and signaling system. Appliances and devices either send or receive signals, which travel through circuits to or from the fire alarm control unit. Emergency control functions work the same way. Let's see how emergency control functions are initiated. Here's a building. In addition to a fire alarm and signaling system, it contains systems that control fire doors, elevators, and more. Let's see what happens when the fire alarm and signaling system detects a fire. While it sends signals to notification appliances and emergency services, the fire alarm control unit sends a signal through a control circuit, or a signaling line circuit. The signal travels to a relay or an output module. The relay or output module triggers a function of a connected building system. Technically, a fire alarm and signaling system could be designed to interact with any system in a building during an emergency. These would then be emergency control functions. But in most installations, there are systems that are commonly included in emergency control functions, such as elevators, smoke control, and fire doors, and systems that aren't. For example, many buildings have a security camera system, but it's unlikely that they would be controlled by a fire alarm and signaling system in an emergency. Before we examine relays and output modules, let's focus on control circuits. Control circuits are essentially the same as a different type of circuit found in a fire alarm and signaling system. What do you think? Which other circuit type in a fire alarm and signaling system is most like a control circuit? Here's a hint. Think about where the signal's source and destination are. Select your answer, then click Submit. That's correct. Control circuits are essentially notification appliance circuits, used to send power to a relay instead of a notification appliance. Just like a notification appliance in some systems, a relay used for emergency control functions can receive a signal sent from a fire alarm control unit as an output. Once the fire alarm control unit has sent the appropriate signal over the control circuit, it's received by a relay. A relay contains a switch with two positions, normally closed, or NC, and normally open, or NO. When the signal from the fire alarm control unit goes through the control circuit, an electromagnet coil in the relay is energized. This magnetic field moves the switch from normally closed to normally open. This switch can then be used to control the connected system. Instead of a control circuit and relay, the fire alarm control unit could also send the signal through a signaling line circuit to an output module. The choice is determined by whether the system is conventional or addressable. Control circuits and relays are part of a conventional system, while signaling line circuits and output modules are part of an addressable system. An output module is essentially an addressable relay. Output modules are addressable, in part, because multiple output modules can be controlled by a fire alarm control unit through a single signaling line circuit. Each output module has a unique address. The fire alarm control unit can use that address when sending a signal to trigger that module. That concludes our brief overview of the basics of emergency control functions in a fire alarm and signaling system. Next, we'll look more closely at the process of mapping inputs and outputs. Unless otherwise noted, all requirements in this lesson are found in NFPA 72, National Fire Alarm and Signaling Code. We'll be looking at requirements in 4 sections of Chapter 21, Emergency Control Function Interfaces, that relate to elevator recall, elevator shutdown, HVAC systems, and door and shutter release. Designing and programming the emergency control functions of a fire alarm and signaling system can be a complex task, and it only gets more complex as a system grows. To keep the process manageable, there's a framework that we'll cover in this section: the input-output matrix. Each row is a separate source that sends signals to the fire alarm control unit. Each column is a specific output, such as a circuit, relay, or output module that can receive a signal from the fire alarm control unit. A designer or system programmer has a choice in every spot where a row and column cross. Take an action, or don't take an action. Let's use elevator recall as an example of how these function in a real design. Before we continue, let's define the purpose and function of elevator recall. Elevator recall is designed to increase the safety of elevator occupants in 2 ways. First, it's important to prevent occupants from exiting an elevator into an elevator lobby in which there's a fire. Second, it's important to get occupants to safety if there's a fire that's about to impact elevator control equipment. In both instances, the elevator recall function will bring occupants to the safest place in the building, typically the ground floor. In the design, this is the designated level. However, if there's a fire in the elevator lobby on that floor, the elevator will bring occupants to an alternate level, typically directly above or below the designated level. Here's a diagram of a simple 3-story building. There's a stairwell on one side of the building and an elevator on the other. Each floor contains 2 rooms, one large room with access to the stairwell and an elevator lobby. Finally, there's a machine room above the elevator hoistway. A fire alarm control unit is located on the ground floor. The building contains smoke detectors in 8 locations. 1 in every room, 1 in every elevator lobby, 1 in the stairwell, and 1 in the elevator machine room. There's also a single manual pull station on the first floor. There are 6 speaker strobes throughout the building. Finally, the fire alarm control unit is connected to the elevator controller via relays. For this example, the elevator has no manual control. What do you think? Which of these fire alarm components would be found on an input-output matrix for this fire alarm and signaling system? Select all that you think apply, then click Submit. Sorry, that's incorrect. The smoke detectors, manual pull station, speaker strobes, and elevator controller relays would all be on the input-output matrix for this system. The goal of the input-output matrix is to document the function of this fire alarm and signaling system, to program the system to respond to emergencies anywhere in the building. All these devices must be included. Next, we'll start to build the input-output matrix, beginning with the inputs. What do you think? Which of these devices will be listed as inputs on our input-output matrix? Select all that you think apply. Sorry, that's incorrect. As initiating devices, the smoke detectors and the manual pull station will all send signals to the fire alarm control unit. We'll focus on alarm signals for now, and how the system will function if there's a fire in any part of the building. Now that we've begun filling out our input-output matrix by listing each manual and automatic initiating device in rows, labeled with their location, we can map the outputs in columns. First, the notification appliances. This system uses conventional appliances on 3 separate notification appliance circuits, or NACs. Each floor is a separate zone. Rather than create a separate column for each notification appliance, we'll only need to add a column for each notification appliance circuit. Then, we need to include columns for elevator recall. While the notification appliances are either active or inactive, elevator recall has 3 states: inactive, recall to the designated level, and recall to the alternate level, if a fire is on the designated level. Again, keep in mind that this example is simplified. A real matrix would likely contain more inputs and outputs. To connect the inputs to the outputs, we need to decide which outputs each input would trigger in an emergency scenario. If we don't want an input to trigger a particular output, we'd leave that box blank. If we do want an input to trigger a particular output, we'd mark that box. Let's walk through the steps we need to take in order to fill out this input-output matrix. First, we want all 3 notification appliance circuits to activate if the fire alarm control unit receives an alarm signal from any of the initiating devices in the building. To do that, we need to mark the intersection of every initiating device row with every notification appliance circuit column. Next, we can make some decisions about elevator recall. Let's begin by defining the designated and alternate levels. In specific emergency conditions, we want the elevator to immediately bring all occupants to either level, whichever is most appropriate. Elevator recall to either level will only be initiated by alarm signals from the smoke detectors in the elevator lobbies and the smoke detector in the elevator machine room. Any fire that would activate the other initiating devices should still trigger the notification appliances, but it wouldn't pose an immediate threat to elevator occupants. In this design, the designated level is the first floor, and the alternate level is the second floor. To keep occupants safe, if an alarm signal is sent from the smoke detectors in the elevator lobbies, on the second and third floors, or the one in the elevator machine room, we'll want to trigger elevator recall to the designated level. If the signal is sent from the first floor elevator lobby, elevator recall will be triggered to bring occupants to the alternate level. When creating an input-output matrix, it's important that the design not be compromised. For example, if the first floor elevator lobby smoke detector sends an alarm signal to the fire alarm control unit, elevator recall is initiated to the alternate level. But what would happen if we also marked the box to send a signal to recall the elevator to the designated level? These two signals would conflict with each other and compromise the design of the system. It's vital that the system operate as designed during an emergency. Verifying the input-output matrix is an important step during both the design process and acceptance testing. Again, remember that this input-output matrix was created for educational purposes and is simpler than one you'd find in the field. As buildings and systems get bigger, so too does the input-output matrix. Next, let's explore different requirements for emergency control of HVAC equipment, doors and shutters, and a deeper look at elevator recall and shutdown. One emergency control function of a fire alarm and signaling system is to limit the spread of smoke. This can be done by shutting down HVAC systems that might move smoke from one compartment to another. In this section, we'll ask you to consider how air flows through an HVAC system in order to understand how they can be used strategically during a fire to reduce the spread of smoke. Pay attention to the terminology used here, as we'll refer to it throughout this section. HVAC systems have a supply side and a return side. Supply implies the supply from the system to a space. Return implies the return of air into the system. The system's air handling unit processes the air, filtering, heating, cooling, humidifying, dehumidifying, or more. Most of the air is pushed back into the space through the air supply, while the rest is pushed out of the system as exhaust. At the same time, the system is pulling air in to heat or cool. Some of that comes through the air return from the space, while some is outside air. To explore this, let's look more closely at requirements for smoke detection on the supply and return sides of the HVAC system. What do you think? Is it effective to include smoke detection on both the supply side and return side of an HVAC system? That's correct. If smoke enters the system at any point, it's important to stop its flow. Therefore, it's effective to include smoke detection on the supply side and the return side of an HVAC system. There are two reasons to include smoke detection on the supply side of the HVAC system. First, the HVAC system itself might cause a fire. Second, a percentage of the air flowing into the system is coming from the outside. This mixes with the air coming from the air return from the space. If the fire is outside, the HVAC system might inadvertently spread that smoke throughout the space. Whether smoke is coming from a fire originating from the HVAC system or from a fire outside the structure, it's important to detect it before it's pushed through the space. It's important to note that NFPA 72 does not contain requirements that determine the detection required for HVAC systems. If detection is needed, this will be identified in applicable building, fire, or life safety codes, and the other codes and standards that they reference. For example, NFPA 101, Life Safety Code, references NFPA 90A, Standard for the Installation of Air Conditioning and Ventilating Systems, which requires smoke detection on the supply side of the HVAC system if the system's capacity is greater than 2,000 cubic feet per minute, or 944 liters per second. It's also common to include smoke detection on the return side of the HVAC system. If there's a fire in the building, smoke from the fire will be pulled into the system through the air return. The objective of HVAC system return detection is to prevent the recirculation of smoke-laden air to other, smoke-free portions of the building via the HVAC system. As you just saw, NFPA 72 doesn't state which systems require smoke detection on the return side. Instead, NFPA 90A requires smoke detection on the return side of systems with a capacity greater than 15,000 cubic feet per minute, or 7,080 liters per second, and serving more than one story. NFPA 72 provides specific requirements for the placement of smoke detectors used for damper closure or full shutdown of an HVAC system. Smoke detectors can be placed either within a smoke compartment or directly inside the duct. These smoke detectors typically send a particular signal to a fire alarm control unit. What do you think? Which signal type is most commonly sent to a fire alarm control unit from a smoke detector used in an HVAC system? Sorry, that's incorrect. Activation of a duct detector will shut down the HVAC system and signal a supervisory condition. Remember, the purpose of a duct detector is to shut down the air handler so it will not move smoke throughout the building. The use of duct detectors is not a method of detecting a fire in an open area covered by an HVAC system. Only if the building does not have a constantly attended location or is not transmitting to a supervising station is the detector permitted to initiate an alarm signal. Next, let's look more closely at the smoke detection equipment that can be included in the design for an HVAC system. This includes area detection in compartments served by the HVAC system, specialized duct detectors, and smoke detectors installed directly in ducts or other HVAC system spaces. Importantly, requirements for the installation of this equipment can be found in standards other than NFPA 72. NFPA 90A requires the installation of smoke detection specifically for the purpose of automatically de-energizing fans of an HVAC system when smoke is detected. As you've already seen, this can be completed with the use of area smoke detection in all of the compartments served by the HVAC system. Typically, however, this is achieved by installing listed duct detectors directly in the ducts of the system. If, for some reason, a design doesn't use area smoke detection or listed duct detectors, NFPA 72 also permits the installation of smoke detectors within the duct, as long as they're listed for the purpose. Using smoke detectors like these is common at return air plenums, as shown in this image. Alternately, these smoke detectors can also be installed directly inside a duct. In that case, they must still be accessible for inspection, testing, and maintenance. Let's test your understanding. What do you think? Which of these statements best describes the function of smoke detection in an HVAC system? Sorry, that's incorrect. As you've seen, smoke detection on the return side of an HVAC system is most effective at detecting a fire in a space served by the system, and smoke detection on the supply side of the system is effective at detecting a fire in the system itself. Finally, the initiation method for HVAC shutdown, or damper or shutter closure, depends on the system used. There are two options: non-computer controlled HVAC and building systems, and computer-controlled HVAC and building systems. Both operate differently, but you should keep one thing in mind as we explore them. Each method must be implemented in such a way that the interface is monitored for integrity. When a building uses a non-computer controlled system for HVAC, the HVAC systems are controlled during an emergency by direct connection from the building fire alarm and signaling system to the respective fan, damper, or shutter that is to be controlled. Power is generally switched on or off via a relay contact or output module located in the fire alarm and signaling system, or near the controlled equipment. It may also be connected to a controlling motor control center, or MCC. These two diagrams illustrate examples of non-computer controlled systems. In the diagram on the left, you can see an interface with the HVAC system fan. In the diagram on the right, you can see the interface with a smoke damper. The computerization of building control systems has led to the integration of these systems with the fire alarm control unit. A computer-controlled HVAC, or other building system, may be interconnected to the fire alarm and signaling system via electrical contacts. These relay contacts may activate fans and dampers directly, as they would with non-computer controlled systems, or they may activate an HVAC system monitored input circuit and an HVAC system control unit. You can see this in the diagram on the left. A computer-controlled HVAC may be connected to the fire alarm and signaling system through a digital data interface, or through a network connection. The diagram on the right shows an example of this. Here, building system control panels are connected to the fire alarm control unit through a local area network, or LAN. Next, we'll explore requirements for the control of doors and shutters by a fire alarm and signaling system, and their related functionality. As you go through this section, keep an eye out for requirements and functionality that are similar to those for HVAC system control. Smoke and fire doors are often held in the open position to allow free movement through buildings. Building, fire, and life safety codes require that the doors automatically close during a fire emergency to prevent the passage of smoke or fire. This is commonly accomplished using the fire alarm and signaling system. When the fire alarm and signaling system is activated, hold open devices are released. Hold open devices are typically electromagnetic units, powered by a supply that's either 24 or 120 volts AC. During a possible fire condition, power to the magnets is cut, de-energizing them. This causes the door to be released and closed. In previous lessons, we've discussed the role of secondary power to a fire alarm and signaling system in addition to primary power. What do you think? Is a door hold open generally required to be powered by a secondary power supply in the event of a loss of primary power? Sorry, that's incorrect. Door hold opens are not required to be on a secondary power source because they are considered a fail-safe mechanism. Loss of power would cause the fire doors to close, which is considered a safe condition. Earlier, we illustrated how smoke detection can trigger the shutdown of HVAC equipment or the closing of dampers in the HVAC system. This can be accomplished by using either a dedicated detector in the ductwork or with smoke detection in the area served by the HVAC system. Smoke detectors can also be used to activate door and shutter release. As with HVAC control, door and shutter release can be triggered by a dedicated smoke detector or by area smoke detection. If installing a dedicated smoke detector, its location and placement must meet specific requirements. We'll take a closer look at those requirements next. To begin understanding how to apply the requirements for smoke detectors dedicated to door release, consider the number of variables in a design. First, consider that smoke may be detected on either side of the door. A designer may need to consider characteristics of two very different spaces for one door. Second, consider the location of the smoke detector. They could be wall-mounted, ceiling-mounted, or even mounted directly on the door frame. Third, consider the height of the ceiling. In many designs, the height of the ceiling on one side of the door may not match the height of the ceiling on the other side. NFPA 72 includes all of these considerations in its requirements. Smoke detectors that are used exclusively for fire door release service need to be installed according to the requirements shown in these diagrams from NFPA 72. Click the diagrams for a closer look. Notice that these diagrams make distinctions between smoke detectors that are mounted on the door frame and those that are wall or ceiling mounted. Then, these diagrams break down requirements by the height of the ceiling on both sides of the door. Each combination is depicted in a separate row. Low ceilings on both sides, high ceilings on both sides, and low on one side and high on the other. These designs are based on the speed at which smoke would be expected to fill one space before spilling over into the other, prescribing smoke detector placement to reduce response time. It should be noted that if the system design included area detection on either side of the door that triggered its release, you would not need to use these diagrams. So far, you've seen requirements for doors that are normally held open, but are shut during an emergency. Another requirement is for door locks. What do you think? Why would it be valuable for a fire alarm and signaling system to be able to control door locks in a building during an emergency? Sorry, that's incorrect. A door that's typically locked may be in an egress path. Unlocking that door during a fire would give occupants access to a necessary escape route. Building, fire, and life safety codes typically list a set of conditions that must be met before an egress door can be maintained in a locked condition. One such condition is that the activation of the fire alarm and signaling system automatically unlocks all doors, thus allowing unrestricted egress from a building. The interface is generally accomplished by connection from the fire alarm and signaling system to a relay that's connected either to the electromagnetic door locking device or to a security system that provides door control functions. As you already saw, the circuit should be arranged to provide a fail-safe operation. In other words, the circuit design must allow release of the door in case of circuit failure, security system failure, or power failure. Now that you've gone through some of the fundamental requirements for emergency control of doors and shutters, think for a moment about fail-safe mechanisms. What do you think? Which of these examples would represent fail-safes? Select all that you think apply. Sorry, that's incorrect. Two of these examples are fail-safes: the locked door on an egress path that automatically unlocks after a loss of power, and the electromagnetic hold open on a fire door. The other two options lead to a secure or compromised condition during a loss of power, not a safe condition. Fire alarm control units commonly initiate one of three emergency control functions in an elevator system by sending a signal to the elevator controller: elevator shutdown, elevator recall, and in-car warnings. You already saw how, during a fire, elevator recall can help occupants avoid exiting an elevator onto a floor where they'd be at greater risk. Elevator shutdown also protects elevator occupants by shutting down an elevator if the fire sprinkler system is going to activate in the elevator machine room or hoistway, compromising elevator components such as the braking system. Finally, firefighters may use an elevator while responding to a fire. They can take control, overriding functions like elevator recall. Because of this, in-car warnings provide them with a warning that smoke has been detected in the control room or hoistway, giving them the information they need in order to know if they should stop using the elevator before it becomes compromised, or before power is shut down by sprinkler activation. What do you think? Which document requires that elevator recall be included in a building design? Sorry, that's incorrect. NFPA 72 does not state whether or not elevator recall is required. Instead, most building, fire, and life safety codes will reference related codes and standards that contain the requirements. NFPA 101, for example, requires that elevators are compliant with ASME A17.1, CSA B44, Safety Code for Elevators and Escalators, which requires elevator recall functionality. Effectively implementing elevator emergency control functions depends on an understanding of the components of an elevator system. Designs may differ, but an elevator will operate in a hoistway above a pit, suspended from equipment in some manner of machine room. Any room into which an elevator opens directly is known as an elevator lobby. One level, typically the first floor, will be the designated level for elevator recall, while another, typically adjacent to the designated level, will be the alternate level. This diagram contains these labels in addition to smoke and heat detectors, in-car warning equipment, and sprinklers. Fire alarm and signaling systems are integrated with elevator control systems to initiate an elevator recall sequence or to initiate a power shutdown. The interface is generally accomplished by connection from the fire alarm and signaling system to multiple relays that are in turn connected to the elevator controller. Each relay or output module represents a singular function. The number of these relays is dependent on the number of actions that need to occur. One for recall to the designated level, one for recall to the alternate level, and one for the in-car warning. The conductors on the output of the relay or output module are not supervised by the fire alarm control unit. To reduce the risk of issues with these conductors, the distance over which the component controlling the emergency control function can be from the relay or output module is limited by NFPA 72 to 3 feet, or 0.9 meters. If the conductors are installed in a metal raceway or metal armor cables, this distance can be increased to 20 feet, or 6 meters. Note that this requirement applies to all emergency control functions, not just those related to elevators. Let's look more closely at requirements for fire detection as a means to initiate elevator control, beginning with elevator recall. NFPA 72 requires elevator recall to be initiated by smoke detection. It also defines specific areas where smoke detectors need to be installed for this purpose. We'll explore the requirements for smoke detection in these locations. But first, what do you think? Which of these are areas where smoke detection could effectively initiate elevator recall? Select all that you think apply. That's correct. Smoke detection can effectively initiate elevator recall if installed in any of these locations. When placing smoke detectors in elevator lobbies, requirements are based on the distance from detectors to elevator doors. Detectors aren't required to be located immediately adjacent to elevator doors, but they do need to be placed so that they're no more than 21 feet, or 6.4 meters, from the elevator door on each floor. For example, look at this diagram. We can draw a line representing this distance on the center line of the elevator door. Drawing an arc from that line, we can see the area that must contain the smoke detector. But what if the design includes a bank of multiple elevators? Individual smoke detectors aren't required for each elevator in an elevator lobby serving multiple elevators. Let's add 2 elevators to the diagram you saw before, each with an arc to show the area that must contain the smoke detector. As long as we place a smoke detector within the space where the areas overlap, the design will be compliant. There are circumstances where smoke detection may not be the most effective way to initiate elevator control. Because of this, NFPA 72 contains allowances for other detection methods in these spaces. What do you think? Which of these are characteristics of these spaces that might make smoke detection less effective? Sorry, that's incorrect. Some elevator lobbies, hoistways, and machine rooms are not suitable environments for the installation of spot-type smoke detectors. Dust, dirt, humidity, and temperature extremes may exceed the operating parameters of the smoke detectors. A spot-type smoke detector installed in the elevator lobby of an unheated parking garage, for example, would likely experience problems due to vehicle exhaust, dust, dirt, humidity, and temperature extremes. NFPA 72 contains requirements that are intended to prevent nuisance alarms from smoke detectors installed in such areas. Another type of fire detector may be substituted for a smoke detector where the authority having jurisdiction, or another code, requires detection in an area with ambient conditions that are unsuitable for a smoke detector. Heat detection is an example of another type of detection that might be used. Next, let's move on to requirements for initiation of elevator shutdown. Recall the purpose of elevator shutdown. There may be sprinklers installed in an elevator shaft or elevator control room. If the sprinklers were to activate, the water discharged onto the elevator and control equipment could put occupants at risk. For that reason, the power to the elevator needs to be shut down before water is discharged onto the elevator or control equipment. Unlike elevator recall, which is typically initiated by smoke detection, elevator shutdown is typically initiated using heat detection or supervision of the fire sprinkler system through water flow or pressure switches. When heat detectors are used, they need to be installed within 2 feet or 0.6 meters of each sprinkler, and they must have both a lower temperature rating and a higher sensitivity than the sprinkler. This requirement helps ensure that elevator shutdown will initiate before the fire sprinkler system does. You can see an example of this in the image shown. In this example, a smoke detector used for elevator recall is on the left, while a heat detector used for elevator shutdown is on the right, located within 2 feet, or 0.6 meters of the fire sprinkler. Think about the usage of initiating devices connected to the fire sprinkler system as a means of initiating elevator shutdown. These may be water flow or pressure switches on sprinkler system piping. In the earlier lesson on supervision in a fire alarm and signaling system, you learned how these devices often include time delays. What do you think? Can water flow or pressure switches used for elevator shutdown include a time delay like those used for sending an alarm or supervisory signal to a fire alarm control unit? Sorry, that's incorrect. While water flow switches or pressure switches can also be used to initiate elevator shutdown, these cannot have a time delay as they need to activate power shutdown immediately upon water flow. They must also be installed as close as possible to the sprinklers that will discharge on elevator equipment to further reduce any delays. Fire sprinklers are a valuable way to increase building, fire, and life safety. But as you've heard, they can pose specific problems to elevator equipment, risking the safety of elevator occupants during a fire. Care must be taken. What do you think? Which of the following people or groups should have input into the design of a fire sprinkler system or fire alarm and signaling system in an elevator hoistway, machine room, or control room? Sorry. Elevator shutdown depends on the functionality of a shunt trip disconnecting means. After a fire alarm control unit receives an alarm signal from a local heat detector, it sends a signal to activate the shunt trip breaker. The shunt trip then disconnects power to the elevator. This functionality depends on the presence of both an output module and input module, or 2 relays. The output module or one of the relays is used to activate the shunt trip disconnecting means. The shunt trip needs power to disconnect power to the elevator. Because of this, an input module or relay needs to be used to monitor that there is always power available to activate the shunt trip disconnecting means. If the power is lost, a supervisory signal is sent to the fire alarm control unit, alerting personnel to the issue. When placing initiating devices for elevator control, a designer must consider the accessibility of the devices for inspection, testing, and maintenance. All devices need to be accessible from outside the elevator hoistway. What do you think? Which of these options would satisfy this requirement, providing effective fire detection and access for inspection, testing, and maintenance? Select all that you think apply. Sorry, that's incorrect. A detector accessible from a rated access hatch through the elevator shaft and an air sampling detector with sampling ports on the inside of the hoistway would both allow for effective fire detection and access for inspection, testing, and maintenance. Even if it may provide effective detection, it would not be compliant to place detectors in such a way that they would require that inspection, testing, and maintenance be performed by personnel on the elevator car. Now we'll give you a chance to put this information together with an activity. In it, We'll ask you 5 questions related to emergency control functions and this elevator diagram. Click Next to get started. First, consider elevator recall. Where would you primarily find requirements for elevator recall in NFPA 72? That's correct. Chapter 21, Emergency Control Functions, contains the primary requirements for elevator recall, though these requirements may contain references to the chapters dedicated to fundamental requirements, circuits and pathways, and initiating devices. Here, you can see that we've added labels to this diagram for the spaces related to elevator control. However, a number of these labels are incorrect. Based on what you've seen so far, which of these labels are incorrect? Select all that apply. Sorry, that's incorrect. The labels for the machine room and hoistway have been switched. Also, while the label for the designated level on the ground floor is correct, the second floor is labeled primary level. This should be the alternate level. This diagram now includes notes for emergency control functions. 6 of the smoke detectors, labeled S1 through S6, have been tied to a specific function, which you can see defined in the on-screen legend. There are several issues with this design. Which of the smoke detectors present a problem? Select all that apply. Sorry, that's incorrect. Smoke detectors 1, 3, and 6 all present issues. Smoke detector 1 is connected to elevator recall to the designated level, but it's on the first floor, which is the designated level. Smoke detector 3 does not initiate elevator recall to either the designated level or the alternate level. Smoke detector 6 initiates elevator recall to the alternate level. Being in the elevator machine room, this smoke detector has no specific reason to initiate elevator recall to the alternate level instead of the designated level. In this diagram, you can see that there's a heat detector installed in the elevator machine room, in addition to the smoke detector. This heat detector is assigned to initiate elevator shutdown. After receiving a signal from the heat detector, what will the fire alarm control unit do to initiate elevator shutdown? That's correct. The fire alarm control unit will activate the shunt trip disconnect. The heat detector in the machine room is located near a fire sprinkler. Both activate when the ambient temperature rises to a set level, which must activate first in the event of a fire in the machine room. Sorry, that's incorrect. In order to keep elevator occupants safe, elevator shutdown must be initiated before the fire sprinklers are activated. The heat detector, being used to initiate elevator shutdown, needs to activate first. This is achieved by using a heat detector that's more sensitive than the sprinkler, with a lower response time index. Great job applying your knowledge. You've completed this activity, and you're almost done with this lesson. In this lesson, you explored how NFPA 72 requirements impact the design and functionality of emergency control functions of a fire alarm and signaling system, providing safety for building occupants during a fire. You should now be able to determine correct fire alarm and signaling system outputs given inputs from select initiating devices. Describe how a fire alarm and signaling system can send outputs to perform emergency control functions, and describe considerations and requirements for the selection and placement of initiating devices within HVAC equipment, fire alarm equipment used for door and shutter release, and initiating devices used to initiate elevator recall and elevator shutdown. Thank you for your participation. You may now proceed to the assessment for this lesson. Now it's time to find out what you've learned. You'll be presented with a series of questions. A score of 70% or higher is required to pass. You'll have as many attempts as needed to obtain a passing grade. Note that there is no audio with the assessment questions. Select the next button when you're ready to begin. You have successfully finished the assessment. Once you complete the course evaluation, you will be awarded your certificate of completion with CEUs. You may now exit the module.